Yeah. Are you able to see the screen shared to you? Is it visible?
Yes, sir.
Yeah.
Yes, sir.
Yeah. Good. So now we will look at a dispersive power of grating and we'll solve some problems based on this. So in the earlier class, we have seen that if this is a grating having a large number of openings and closings, suppose say I have a grating like this, and these are the openings and closings, parallel lines, many parallel lines are there. Then I suppose that a light is incident on it. And the light, whatever incident on it, suppose say it is a white light. So when white light is incident on it, suppose say a white light is incident on it. Because we have seen grating equation, lambda is equal to sine theta by n into n. If you see this equation, the lambda wavelength, if changes, theta also changes. That means different colors will have different angle of diffraction. So the angle of diffraction is not same for all lambdas. As lambda changes, theta also changes. If I take white light, okay, white light is a constitution of several colors or seven colors we say. Therefore, among these seven colors, if you take, okay, different colors among this, you can now suppose that, okay, the light which is coming here is a composition of seven colors. Therefore, these seven colors will undergo straight away violet comes, suppose say, and then okay, violet goes like this by an angle equal to theta v, and red light goes by another angle by an angle called theta r. Therefore, as lambda changes, the angle of diffraction also changes. Hence, thereby, a white light is falling on a grating. It separates out the colors symmetrically from the center on either sides and separates out the color because the angle of diffraction is different for different colors. Therefore, a spectrum is formed, spectrum is formed, okay, by the grating is formed by grating, okay, due to different diffraction angles. That's the phenomenon of diffraction. But you can see that the variation at the rate of variation of angle of diffraction, okay, with wavelength is different, and therefore the separate spectral lines, these are called spectral lines. Violet color, different colors they are coming out, they are called spectral lines. So they are different. Therefore, we have a dispersive power for, yeah, I'm sharing it again. Hence, you should know that the angle of diffraction is different for different wavelengths. Hence, how the wavelengths are undergoing a different, okay. So this is the dispersive power I am taking. This is dispersive power. So now we will define a dispersive power of grating. So the dispersive power of grating is
Sir, your
defined
voice was
as,
breaking, sir.
yeah, is it visible? Can you see the screen share, all of you?
Yes,
Is it
sir.
visible?
Yes, sir. It is visible.
Can you see the screen?
Yes, sir.
Yeah. What is the problem? Any problem?
Voice was not clear, sir.
Okay. Okay, just a minute. Maybe due to technical problem with the internet. Is it okay now? Can you hear me properly?
Yes, sir. Now is clear.
Yeah. Now, dispersive power, if I talk about it, okay, the wavelength, different wavelengths will undergo different angle of diffraction. Therefore, in the white light, different colors will undergo different angle of diffraction. Hence, the constituent colors in the white light will get separated out because of this. Hence, now here I would like to define dispersive power. Dispersive power is defined as the rate, okay, how much the rate of variation. Okay, what are the variation I'm taking? I'll take a rate of variation of angle of diffraction. Angle of diffraction. How it varies with wavelength. That we call it as the angle of diffraction. Okay. So all of you mute yourself. Some of you are unmuted and we are getting some disturbance. Yeah. Now look at this. The rate of variation of angle of diffraction. Okay. So I'm going to see this. The rate of variation of angle of diffraction with okay, the wavelength is called dispersive power of grating. Dispersive power of a grating. And generally, if you see this of a grating, and it is represented, we represent it by the change in lambda theta. A small change in theta will occur when there is a change in lambda. D theta by d lambda we have. If you have a formula, we have seen that lambda is equal to sine theta by n into capital N. So it follows that lambda is directly proportional to okay theta, the angle of diffraction. Angle of diffraction. Therefore, if theta means if the color changes, angle of diffraction also changes. So angle of diffraction is not the same for this. Hence, here I'll write the equation, grating equation. We have grating equation we have seen in the earlier class also as E plus D sine theta is equal to n lambda If I differentiate this equation, I'll get E plus D sine theta differentiation is cos theta and theta derivation is d theta with respect to theta is equal to n number of order into d lambda with respect to this. And thereby I will write here d theta by d lambda d theta by d lambda. D theta by d lambda is equal to n by okay e plus d into cos theta. This is we call it as okay dispersive power. Dispersive power is now represented by d theta by d lambda. Okay, so this is the expression for this. D theta is by d lambda is equal to n by e plus d into cos theta. So therefore, the variation of diffraction angle with lambda is called dispersive power. Then it is represented by d theta by d lambda. Now we have derived this as n by e plus d into cos theta. So we will solve one problem based on this. So am I audible, all of you?
Yes, sir.
Can you see the screen also?
Yes, sir.
Yeah. Now, based on this formula, dispersive power is nothing but how effectively the grating separates out the various lambdas by providing different angle of diffraction. So therefore, we'll solve one problem based on this. So make a note of the problem one. A diffraction grating has 15,000 lines per inch. Calculate dispersive power of grating in the third order when the incident light has 5,000 Armstrong wavelength. Okay. This is the problem we have to solve it. Now we have seen that the formula for this, okay, is, we have seen the formula dispersive power is given by d theta by d lambda is equal to, we derived it, n by e plus d cos theta. Okay. Therefore, here, whatever they have given, we will write it. But before that, we want theta value. Theta they have not given. So we have to find theta value. To find theta, I am using L lambda equal to sine theta by n into n, from which I can write, okay, sine theta is equal to lambda n into capital N. So lambda they have given as 5,000 Armstrongs. So I'm writing this as this. Into n, they're asking for third order. So I have lambda 5,000 and third order is 3, and they have given number of lines per inch. 15,000 lines are there per inch. I convert it to centimeters by dividing 2.54. So can you tell me how much do you get the value of sine theta from this? Anyone? How much are you getting sine theta value? Row number 22, can you tell me the answer?
Yes, sir. Let me multiply it,
Yeah,
sir.
yeah, multiply it.
Yeah.
Prasanna, 29, have you done? 28, Fanikumar,
Yes, sir.
how much is the answer for this? $52, row number 50,
0.88.
0 point
88.
0.88. So if 0.88 is sine theta, what is the 0.88? 6. I'll just, okay. If sine theta is there, what is the cos theta value? How much do I get? Cos theta.
0.46.
0.46.
0.46. 8.
of 4. Okay.
464, sir.
So we got now cos theta value here. E 1 plus E by D is nothing but N, as we have seen in the earlier class. Okay. So we have d theta by d lambda is equal to N into E plus D is called grating element, and we have cos theta, which is nothing but we know that 1 by E plus D grating element is I think number of slits N. So I can write this is N by cos theta. So we have all the values to find out the dispersive power of the grating. So dispersive power of the grating d theta by d lambda, okay, is equal to N third order capital N. They have given 15,000 by, okay, 2.15,000. They have given divided by 2.54, okay, N into N into 1 by cos theta. Cos theta is 0.464. So what is the value we are getting from this? Followed? 1 by ED is capital N. So 1 by ED I have changed this and I have written as capital, okay. This 1 by ED is this. I have written this as capital N. So how much are you getting?
38,182.
3818
3818.
2.1.
Okay, that's it enough. Okay, this is the dispersive power of a grating. Okay, so we will do one more problem based on this, but before that we'll see one more concept, and we will do problem based on both. So, and then now we will look at another concept called resolving power of a grating. What is the resolving power of a grating? This is very important. So you studied about sodium vapor lamp. Sodium vapor lamp, which gives you two wavelengths, lambda 1, lambda 2, and these lines you called it as D1, D2 lines. Have you heard about this D1, D2 lines? And these are of course yellow color. Yellow color. Now you assume that you are looking at a white light, and white light is a combination of 7 colors. And if you look at with your eye, you cannot see these 7 different colors unless until that white light is passed through some device. If the white light is passed through a grating, as we have seen, okay, this is the white light if I'm taking, and this white light will be divided into different colors, as you know, okay, by the grating. So grating will do it. So that means if it is a white light, I'll get here different colors coming out of like this. 7 colors will come out of this. That means grating has a capability to see 7 colors as 7 different colors because thetas are different. Theta 1 for violet, theta, okay, Y for yellow, theta green, and we have theta R for red color, and we have blue color, likewise we have. Therefore, but our eye has not that much sensitive to see the closely spaced wavelength as separate wavelengths. So therefore, we use some devices like grating or prism to see the closely spaced lines. In the lab also, when you have uh, done some experiments, you observe that there is a yellow lamp called sodium vapor lamp, which is giving 2 yellow colors. But our eye cannot recognize these 2 different shades of yellow as 2 different lines. We have seen only uniform yellow. Therefore, our human eye has some disability or not capable of, okay, observing different, slightly different colors as two individual colors. But if you take the sodium vapor lamp yellow color, okay, so I now take, suppose a yellow color. If yellow color is incident on a grating, this is the grating, okay, then this grating will give you two yellow shades. This is 0.1 yellow will be something like this, and they will give you another yellow also, which is something like this. This is another yellow. Two yellows will be there. It will show two yellows as two different colors. And among this, one of the yellow will have 5890 Armstrong units. The other yellow given by the light, okay, by sodium vapor lamp is 5896 Armstrongs. A difference of just 6 Armstrongs, where our eye cannot differentiate these 6 Armstrongs, therefore we see as a single yellow color. Therefore, we have another important parameter called resolving power of a grating. The resolving power of a grating is the ability of the grating to show two closely spaced spectral lines as two different and individual distinct lines, okay, for which our eye has no such capability. So thereby we'll have the ability of the optical instrument to show two closely spaced objects as two distinct objects is called resolving power. So I will now define the resolving power for any object, any optical instrument, not only for grating, but in specific we'll see the grating equations. Okay, so I write here the ability, so I take it as the ability or capacity, you can write it as the ability of an optical instrument like grating, prism, etc. Okay, the ability, or a telescope or a microscope, the ability of an optical instrument to show two closely spaced, very closely spaced, where our eye cannot recognize as two objects, two closely spaced, okay, objects. Here objects means maybe spectral lines also, you can use it. The word spectral lines means different colors. To show two closely spaced objects as two distinct, okay, or different, we say distinct objects, okay, is called resolving power. Resolving power. So for grating, how do we see here? If I show up there are sodium light will have D1, D2 lines, which we cannot recognize, but grating can show these two lines as two separate lines as D1 and D2 lines. So that is the ability of the instrument to show two closely spaced objects as two different objects. Now we will see how I can get this. So there is a criteria given by a scientist called Rayleigh, and that we call it as Rayleigh criteria, Rayleigh criterion, okay, criterion for resolving power. So which states that, suppose say I have here two wavelengths D1, D2, if you see in sodium vapor lamp. In that two wavelengths, we have lambda 1 and lambda 2. Lambda 1 and lambda 2, both of them will give you diffraction patterns. So therefore, we have sine theta by n into n. But for lambda 1, we have theta 1. Okay. And similarly, if I do lambda 2 is equal to sine theta 2 by n into n. Here, small n is order constant, maybe first order for both lambda 1, lambda 2, and capital N is the number of lines for the grating is fixed. Capital N is fixed. Therefore, as lambda changes, theta changes. Okay. Now, that means this lambda 1 will produce diffraction effect and gives you a diffraction effect, suppose say maybe something like this. And lambda 2 also gives a diffraction effect, maybe not be exactly same, but maybe slightly different and giving like this. Okay, they will give you different diffraction patterns. They may be going like this, falling like this, maybe like this. So this is the diffraction pattern due to lambda 1. This is the diffraction pattern lambda 2. Therefore, if both are formed simultaneously, the resultant we will see. So thereby, if you want to see them separately, these two diffraction patterns should not mix. That means lambda 1 pattern should be something like this, and lambda 2 pattern should be, it's okay, I'll see the lambda 2. Suppose say lambda 2 pattern may be overlapping here, but I have the peak, central peak different. If the grating is capable of giving two separate peaks like this, I can see the two wavelengths as two separate wavelengths. If they overlap, I cannot see it. Therefore, we have a criteria, okay, given by Rayleigh, and that will give you the idea of the resolving power of a grating. So the Rayleigh criteria simply states that, okay, two spectral lines, that is lambda 1, lambda 2, that two spectral lines, or we say two closely spaced spectral lines, I'll write instead of that. Two, okay, closely spaced spectral lines. Here in the case of sodium vapor lamp, lambda 1 and lambda 2, lambda 1 is one line, then lambda 2 is other line. Closely spaced spectral lines, okay, are resolved. Only we can see them as two separate lines by using a grating, or resolved, okay, into distinct lines. Distinct lines by a grating. I'm writing here grating, or any optical instrument also you can take, by a grating, when, okay, the central maxima, that is this is central maxima, central maxima, due to one spectral line. One spectral line means lambda 1. This is the lambda 1 spectral line. This is the lambda 1 spectral line. One spectral line falls over the first minima of the other, and vice versa. This you may not be simply digested it, understand it, but if I draw the figures, you can easily understand it. So I will show how these two can be shown. Now I am taking here the pattern. This is the, okay, we have minimas. This is the maximum, and this is the diffraction pattern due to lambda 1. Suppose this is the lambda 1. Now suppose the source have second wavelength also, and I am representing second wavelength also. The second wavelength, suppose say, as a diffraction pattern, something like this, it is almost here, but slightly coming and giving you a pattern like this. And suppose say, this is lambda 2. These two wavelengths are there in the same source. And two are producing two different diffraction patterns, but they are very, very close. And therefore, if I want to see the resultant is the superposition of these two. Therefore, I'll get some resultant, add them, I'll get resultant, and this is the resultant of it. This is the resultant. So resultant is giving you only one peak. That means I can see that there is only one wavelength. Therefore, this condition is called as not resolved. That means this is not resolved condition. It is not able to show two wavelengths lambda 1, lambda 2 as two different wavelengths. That means the diffraction pattern of lambda 1 and lambda 2 are in such a way that they are almost falling in the same positions, and therefore resultant is something like this. You cannot see it. Now I will go for another one. Suppose say this is the diffraction pattern given by one wavelength. I call it as lambda 1. Okay, lambda 1 has given.
Sir,
Yeah,
sir, can you add Nihal into this, sir? He got exited. Now he can't get
yeah,
into.
just a minute. Ask
Yes.
them to log in again so that I can
He requested you, sir. Just look at the
but
bottom of
request
the.
is not there still. Request is not there. Ask them to request again.
Yes, sir.
Okay. So ask them to do it. I will just add you.
Yes, sir.
Okay, now I will see this is a lambda 1. Now I take lambda 2 diffraction pattern also. So I will now choose lambda 2 diffraction pattern. Now lambda 2 diffraction pattern is something like this, and it is going somewhere here, and suppose say this is the diffraction pattern due to lambda 2. No, they are not exactly falling. They are exactly falling here if you see. They are slightly different. Therefore, I now take the resultant. Okay. Yeah, still Nihal has not requested me. Ask him to join by himself. He can also join.
Sir, once go into suggestions, sir. He can't request you to.
But
Have to.
here there is no, I am unable to see him. Do one thing, ask them to log out of
Yes, sir.
the,
There suggestions. Okay. There is no. Okay.
yeah. Ask him to log out completely and again log in.
Yes, sir. Okay.
He can do it. Okay. So now if I go for this, I have now two wavelengths lambda 1, lambda 2 whose diffraction patterns are formed by the grating slightly different. Therefore, the resultant will be something like this. Okay, goes the goes here and goes here, and there is a dip fall and comes here and here comes. This is the resultant one. This is the green is the resultant one, and therefore there is a dip here. Therefore I can see two peaks, separate peaks, and hence the two wavelengths can be seen slightly, but still they are not much. Therefore this condition is called just resolved condition. Just resolve. I want to see the two wavelengths fully and completely. Then the condition of the condition given by the Rayleigh is important. What Rayleigh is saying, see it. If you want to see them sleepily, the central maxima of one due to one spectral line should fall on the first minimum. Likewise, I have to take it. Therefore, I am drawing the figure again, something like this. Suppose say this is the diffraction pattern given by one of the wavelength. One of the wavelength has given the diffraction pattern like this. And we say this is the first minima. This is the first minima. This is the first minima. And if the diffraction pattern produced, by the lambda, this is I say lambda 1. lambda 2 is producing in such a way that, okay, the minimum of this, that means this is the first minimum. At the first minima, if this is the first minima, at the first minima, if you have this exactly, okay, so exactly it should fall in the first minima, we have a maxima like this. Okay, then the resultant, I will draw the both of them again. If you see it clearly, okay, I can write something like this. This is the one wavelength that was I am getting. Okay, this is the minimas, this is the central maxima, and this is the minima due to lambda 1. I call it as lambda 1. Now I take another wave, okay, wavelength, and suppose say that is in such a way that this is the first minima I am taking here, and this comes here, and first on the first minima central maxima should fall, exactly falls and goes here. Okay, this is lambda 2. Then if I take the resultant will be something like this, comes here, goes here, and it's a very deep flow is there, and comes here, comes. Therefore, I can see them as two separate ones. This is called well resolved. Well resolved means, okay, you can see the two wavelengths separately. Therefore, the criteria for looking the two wavelengths, closely spaced wavelengths as two separate wavelengths is that at least the central maxima should fall on the minima of the one. Then the two lines are separately seen. This is called the Rayleigh criteria for the criteria for the resolution. And otherwise, you can also write here the statement something like this. The statement is that grating, okay, whatever I'm taking the grating, I take here, okay, grating resolving power, if I want to define the grating resolving power, resolving power is defined as the capacity to form separate diffraction patterns, or we say diffraction maxima of two closely spaced wavelengths, okay. So grating is a capacity. So the capacity as defined as a capacity to form separate diffraction patterns of two closely spaced wavelengths, separate patterns. Okay. So then we define lambda by d lambda as resolving power. Dissolving power is called this. Therefore, we write lambda by d lambda is the resolving power. For a given mean lambda, if there is a change in lambda, this must be equal to n into n. This is the condition for the resolving power. So this is the condition we require for resolving power. See, resolving power is lambda by d lambda, whereas the dispersive power is d theta by d lambda. These are different. Those are not the same. D theta by d lambda is the dispersive power, and if you see, this is the case for lambda equal to n into n. Otherwise, you can write lambda by d lambda is equal to, we have E plus D sine theta is equal to n lambda. From this, n I can write as E plus D sine theta, okay, n I am writing by, because n is nothing but from this, if you take lambda other side, E plus D sine theta. So I can also use this formula to calculate the, this is the form. Lambda by d lambda is called resolving power. D theta by d lambda is called the dispersive power. Ed sine theta by lambda into n. Now we will do one problem on this. Okay. So it's a very simple problem, but we will do this. A grating, okay, a monochromatic light. This is not based on this, but it's a simple problem. Based on this, we'll do another problem on this. A monochromatic light has a wavelength this, okay, and grating wide of 2 centimeters. We know the lines per centimeter grating, but he is giving that the grating itself is of 2 centimeters wide. This is of 2 centimeter wide they have given. Okay, we have a number of lines on this. Now, what is asking? The wavelength lambda they have given. Lambda is 6560 Armstrong units, so minus 8 centimeters. And grating length they have given, and the first order n equal to 1, and theta angle of diffraction they have given as 20 degrees 22 minutes. And how many lines are there? That means what is capital N they are asking. So we have simple formula, lambda is equal to sine theta by n into n. So he's asking to find what is n. So n is equal to sine theta by small n into lambda. So this is sine of theta given as 20 degrees 22 minutes by n, third order, yes, okay, which order is given? First order, n equal to 1. So 1 into lambda they have given as 6506 into 10 to the power minus 8 centimeters. So I'll get n when. How many am I getting n? Can you tell? Yeah, row number 28.
Sir,
Yeah. Yes. Roll number 4, Ananya, can you tell me the answer? Thirty-two. 32.
Sir,
What is the answer? 42. Anyone, have you done the n value? We will get this as around 5,000 lines, 5,304 lines per centimeter. This is per centimeter, but is asking to calculate for 2 centimeter wide grating. Therefore, for 2 cm wide grating, how many lines do you have? Wide grating, we have 2 into 5304 lines. So therefore, we have 10,680, 608 lines per centimeter. Lines.
Sir, should we convert minutes into degrees, sir?
No need of that, because I have not given point. It is not 20.2 degrees. Okay. If that is the, if you want to write in terms of point, then you have to convert by dividing by 60. Okay. Then in the calculator, you have to enter as 20 point something. But in the calculator itself, you can directly enter degrees and minutes also. Did you follow? There is a provision in the calculator to enter degrees and minutes. If there is no provision,
Yes, sir.
then convert 22, divided 22 by 60. What are the value you are getting? That can be put as a point and you can enter it also. Followed? So I'm going for the next problem. The grating has 15 centimeter length, rule 6,000 lines per centimeter. Find the resolving power. It's a very simple problem. You know that resolving power, lambda, if you take it, okay. So lambda will be, if you take lambda value, lambda by d lambda is the value of resolving power, which is given by n into n. So here n is given first order. This is the first order, n equal to 1. Lambda, capital N they have given. Capital N they have given as 6,000 lines per inch, lines per centimeter, no need of conversion. But they have given that it is 15 centimeter wide. Therefore, 15 into 6,000 lines will be there on the grating. That is, okay, that I should write here. So we have 1 into n now will become, okay, 15 centimeters wide. Each centimeter is having 6,000 lines. So I should write it as, and I'll get the answer as 90,000. Okay, that is important. This is lines actually. This many, this is the lines per centimeter, but n now will having 15 centimeter wide. Therefore, under 15 centimeters, each centimeter will have 6,000. Therefore, 15 into this one gives you the total one. That is lambda by lambda. And next important problem is, okay, you just look at this problem. A prime transmission grating produces angular separation. They have given angular separation. So angular separation for the solution I'm writing here, d theta they have given. Angular separation is 0.01. Okay. And between two wavelengths at an angle of, so angle of diffraction theta they have given 30 degrees. And if the mean wavelength means lambda they have given as 5,000 Armstrongs they have given centimeters. Calculate the difference between the two wavelengths. What is d lambda they are asking to calculate. So we have a formula for the dispersive power. D by is called dispersive power.
Sir, one show the last question, sir. I didn't get it.
This one?
Yes.
Yeah.
What is that 15 centimeters into 6,000 is equal to?
Because see, the grating has a length of 15 centimeter surface. And there are 6,000 lines per 1 centimeter. So therefore, grating is of 15 centimeters length. Per each centimeter, I have 6,000 lines.
Yes, sir, I got. Yeah.
Therefore, I have to multiply. How many lines are there on it? Now next problem is called d theta by d lambda is called dispersive power. Dispersive power gives how the variation occur, the rate of variation in diffraction angle theta with the variation in lambda, dispersive power. So, but we have seen the formula for d theta by d lambda is equal to n by e plus d, okay, cos theta is the formula we have. Now, I have to find this in some simple form. That is, we have lambda is equal to sine theta by n into capital N. Okay. Therefore, you also know that 1 by ED is nothing but capital N. Therefore, I'll write capital N by cos theta. Since we know that 1 by E plus D is equal to capital N. and we have lambda is equal to this formula. Okay, and I am using now these two into that. Thereby I'll write d theta by d lambda, that is dispersive power is equal to n into, okay, here capital N. From this I write capital N is equal to sine theta by n into lambda. So I'm taking this n the other side and I'll take lambda here. Okay, therefore I'll get this. If I get this, I can now write this as simply, okay, if I go for this, I will write like this. D theta by d is equal to, okay, I'm writing it again. So d theta by d lambda is equal to, I have, if I substitute everything, I will get here n into, okay, n into sine theta by n lambda is capital N, okay, by cos theta divided by cos theta. So I'll get sine theta by cos theta, n in get cancels, therefore lambda goes up. Okay, if you see here, n and n goes out. I have sine theta by cos theta. Sine theta by cos theta is, what I'll get?
Tan theta.
Tan theta by lambda, because lambda is here. Okay, so d theta by d lambda is now tan theta by lambda. So he is asking to find out d lambda. So d lambda, if I want to find out d lambda, because difference in the wavelengths is d lambda. How much is d lambda? If I want to find now d lambda value, okay, I take d lambda. I write now this as here. Okay, the left out is that here d theta by d lambda is equal to tan theta by lambda, we got it as. And from this I'll write, okay, lambda into d theta, okay, lambda into d theta by tan theta. If I take, I'll get d lambda. Okay. So I want d lambda. So I'll take the other side, this other side, I'll take it, and this I'll give you this value. So therefore, I'll get d lambda is equal to lambda given is 5000 angstroms. So I'm getting 5000 10 to the power 8. D theta given as 0.01 radian by, okay, the theta they have given. Okay, theta is 30 degrees. So I write tan 30 degrees. If you see the problem here given, okay, d theta is 0.01 radian, theta is 30 degrees, lambda is this, asking to find d lambda. So if I have this, you can find d lambda value. So can you tell how much you are getting from this? Anyone?
Sir, 8.66 into 10 minus 0.
Yeah, that may be around 86.6 Armstrong units.
Yes, sir.
Yeah, that is correct. Okay, I'll stop here after doing just one last important problem. Okay, we have, okay, one more important problem. Look at this. So all of you listen carefully, that today at evening 5 o'clock I will conduct a Moodle practice test just for 5 to 10 minutes. You can log in and do it. Can you do it at 5 o'clock, or can I keep it at later 6 o'clock or 7 o'clock?
Sir, keep it at 7.
7 o'clock?
No, sir. Today we have BM also, sir.
We have 4 o'clock?
BM mock test also, sir.
Okay, at what time? Do you require
7
mock test?
o'clock.
7.
No, I think you have a practice
Yes,
date. Is it
our
necessary to keep?
practice, no, sir.
Yeah.
Does those marks count or?
No, no, it will not come. They will not. This only for practice how to use models. That's all.
Yes, sir.
Sir,
Yeah. Okay.
can you keep at 5 o'clock?
No, 5 o'clock I am ready. But if you have any other tests, it's no problem.
5
That
o'clock,
is
sir,
No,
5.
sir.
okay. Shall I keep it 5:30?
Yes, sir.
Yeah, sir.
Yeah.
Sir, okay.
So 5:30 p.m. you have mock test. Okay, on models. Just is only 5 questions will be there mock test on models. Okay.
Yes, sir.
Okay, sir.
Okay. So we have that is 1901 2020 22. Okay, at 5:30 p.m. we have a mock test. Now you see the last problem. Then I will close the class. The last problem is that a diffraction grating with the 15,000 lines per centimeter is illuminated by sodium vapor lamp consisting of two wavelengths D1 and D2, and calculate angle at which first order maxima due to lambda 1 occurs, angular separation between first order and resolving power. Okay, so this is one of the easiest problem you can do by like this. So they're asking to find lambda 1, but you should remember for sodium, okay, vapor lamp, if you take it, you should remember these values. Lambda 1 will be 5890 Armstrong units. That is lambda 1 they are giving. Or 5890 into 10 to the power minus 8 centimeters. Okay. And next, if I want to write lambda 2, the D2 line is 5896 Armstrongs. The only 6 Armstrong difference between these two yellows. 96 into 10 to the power minus 8 centimeters. And first bit, if you look at, is asking first order, okay, A bit, n equal to 1, first order, maxima due to lambda 1 is 5890 into 10 to the power minus 8. Angle at which they are finding what is theta. So we have our regular formula for grating. The regular formula for grating is lambda is equal to sine theta by n into capital N, which gives you that, okay, sine theta is equal to n into capital N into lambda. So therefore, I can write now sine theta value is equal to lambda 58, lambda 1 I should write here, lambda 1 I should write here, into 10 to the power minus 8, and n equal to 1 order, first order. Order is first, then I should write capital N. Okay, capital N is given as 15,000 lines per centimeter. Okay, so they have directly given, sorry, not centimeter, this is per inch. This is per inch. So therefore, n equal to capital N is 15,000 lines per inch is 2.54. If you simplify, I'll get sine theta value as roughly equal to 0.3478, from which theta is sine inverse of 0.3478 and comes out to be around 20.35 degrees. This you know it easily, you can do it. Okay, and bit B is now angular separation. That means d theta. They is asking what the angular separation means. They are asking to find out d theta. So to find d theta, we have dispersive power formula. That is d theta by d lambda is equal to n by e plus d cos theta, where I'll write this is n into capital N by cos theta. Okay, so therefore I want to find out d theta is equal to n into capital N into cos theta multiplied by d lambda. Okay, which I'll get here. N is now first order, so I'll write 1. Capital N is 15,000, okay, by 2.54. divided by cos theta. Cos, okay, theta we have found it as this cos theta value. So cos theta is 20.35 degrees. Then into d lambda is 6 Armstrongs. Since if I know d1, d2 lines, the difference, if you see it, d lambda is 96. So I'll write as 6. Thereby, I'll find d theta value. How much are you getting d theta value?
0.193.
0.193. Is it you have converted this Armstrongs into 1?
Yes, sir.
Okay. So this may be, I'll write it as 6 into 10 to the power minus 8. Yeah, how much are you getting? Can you tell me again?
0.19.
Point
193, sir.
0.192. Any other value? Somebody is telling different value.
Sir, I got 3.779.
That's all. 3.779 something into 10 to the power minus 4 radians you'll get.
Yes, sir.
This is correct. You check this answer for
Yes.
0.192. Huh? This is not correct. This is correct. D theta value. This is the value. Then C bit. It's very simple bit. Resolving power. Okay. So C is resolving power. So we have resolving power lambda by d lambda is equal to n into Kaplan. So this is n is 1. Kaplan they have given us 15,000 by 2.54. So that will be the answer. So this is resolving power. And this is resolving power. Uh,
590.5.5.
5905.
5.5.
Okay.
Yes, sir.
Yeah, that is lambda by d lambda is the resolving power. Okay. So I stop here this class and I will share you the notes for diffraction, this notes and previous class notes also. In addition to that, I will share a diffraction notes just like interference notes by today itself. Okay.
Okay, sir.
Okay. So I'm leaving here, all of you. Is it okay?
So when we have
Okay,
to
sir.
submit notes?
Notes, because from tomorrow onwards you are having your internals. After the internals you submit.